Yes, it was back in the mole unit though, so it was like way back in September. So you might be like, I don't know, which is one of the reasons why I like doing the gas unit, is because you get to review some of these concepts, right? There's a little poem, if that's helpful. I guess I shouldn't start until the bell goes. Good morning, Baran. I'm good. How are you? Great. We're trying to dredge our brains and see if we can come up with something from September. We're given the percent composition of each element in a compound and its molar mass. How would you find the molecular formula? First of all, what is a molecular formula? The formula, how it is not simplified. Yeah, it's the formula. It's just the formula of the compound. It isn't simplified. It's not the simplest formula. What is the simplest formula? Empirical. That's the empirical formula, okay? So this is the true formula. Like the actual formula. And the empirical formula. I know I said something to do with like the empirical formula is the simplest. What is it? It's the simplest ratio. What kind of ratio? Can I have decimals in it? No. No. It is the simplest whole number ratio of atoms in a compound. Now, in order to find a molecular formula, you must first find the empirical formula. Now, if we're finding the simplest whole number ratio of atoms, instead of using atoms, what could we use? Sorry? We could use mass, but we would need something in between. Pardon me? Moles, okay? So instead of like directly using atoms, we can use moles. And the way that we get to moles is from the, well, we would use the molar mass. And what would we need in order to start with? We would need the grams. Okay, we would need the mass, the grams. Now, if you are given percentage of each element, you can get mass, because what you do is you take the percent and you convert it to mass. And remember, you're going to have to say, assume something. Sorry? Yeah, assume we have not 100%, but 100 grams of the compound. Because the actual mass is not given. I mean, it might be under certain circumstances, but then you'd have to work with that. But if you're given percentages, assume we have 100 grams, and then percent is equal to the mass, right? So we convert the percent to mass. And then we take our mass and we convert it to moles. And then what do we do with that to find our simplest whole number ratio? We divide by the small. And then we times till whole. Okay, so if you don't get whole numbers after step 3, 1, 2, 3, 4, if you don't get a whole number, you would have to multiply until you get a whole number. All right, well, having gone through that, shall we try an example with some ideal gas law stuff attached to it? Hi. Sorry. Can I help you?
Do you have a minute?
Well,
I don't know. No, you're teaching.
Okay.
No.
Okay. All right. So we are going to go then to, where the heck were we? 13.2 D. No, E. Yep. And that is on page 31. Do you want to do this together or do you want to do it on your own? Together? Okay. So percent to mass. Well, we are told, where do we have a percent? We are told that we have 85.63% carbon. And we are told that this gas is composed entirely of carbon and hydrogen. So we know the percent, which is carbon. And if it's carbon and hydrogen, how much hydrogen do we have? Yeah, we have 100 minus 85.63, which is 14 point something. 100 minus 85.63 is 14.37%. And then, before we start on our little poem, what do we need to write? Yeah. Assume we have 100 grams of the compound. And what that means is that we would have 85.63 grams of carbon and 14.37 grams of hydrogen. So we have now done percent to mass. We're going to do mass to moles. Okay, so we want to find our moles of carbon. 85.63 grams of carbon times 1 mole per 12.01 grams. Moles of hydrogen is 14.37 grams times 1 mole per 1.008 grams. And we get 85.63 divided by 12.01 is 7.1299 moles of carbon. And for this one, we have 14.37 divided by 1.008 is 14.256 moles of hydrogen. So now we have converted our mass to moles. And then we divide by the smaller one. And remember, you cannot just say, what would happen if I did this? Is this good? Can I do that? No, because otherwise that would say that this calculation is equal to 1, which it isn't. So what we're going to do is I'm going to just put a little line here, and I'm going to be like, okay, I'm going to divide by 7.1299. Okay, and so that's going to give me 1 here, and 14.256 divided by, I can tell it's a 2, 7.1299 is 1.999, which rounds to 2. So we divided by small. Do we need to multiply? No. What kind of numbers would you get where you have to multiply? What would be some normal decimal places you would have? Yeah? Yeah, you could have like a 1.5, you could have a 2.333. Okay, so you'll have either something that's a third or a half or 1.75 or 1.25, 3/4, 1/4, or 1.667, 2/3, things like that. Okay, things where it's going to be easy to figure out. You're not going to have to multiply by anything other than 2, 3, or 4. Okay, and that means that our empirical formula is carbon, we have 1 of them, and hydrogen, we have 2 of them. And wouldn't it be nice if we were done, but we're not. We need to find our molecular formula. How do we find a molecular formula? Let me go back here. Oh, not that one. We need to find the molecular formula from the empirical formula and the molar mass. Do you remember how to do that? Well, let's remind ourselves, remember the empirical formula is the simplest whole number ratio, and the molecular formula is the actual true formula. How do those two relate to one another? Yes, the molecular formula is a multiple of the empirical formula. It could even just be the same thing. It could be a 1 multiple, but the molecular formula is a multiple of the empirical formula. How would we figure out what that multiple is? Like whether it's a 2 times or a 1 times or a 3 times, what would we need?
Molar mass
Molar mass of
the empirical.
What would we do with that? Let's see if that works. Well, let's not worry about what we have. We're just talking in the abstract here. Does this work? No, why not? Which one of these is a bigger number and which is a smaller number? This is going to be the smaller, and this is going to be the either the same or bigger. So yeah, we'll flip that upside down. So we want the molar mass of the molecular formula divided by the molar mass of the empirical formula, and that's going to give you some value, n, and then you'll take your empirical formula and multiply by n, and that will give you your molecular formula. So two things we need. We need the molar mass of the molecular formula, and we need the molar mass of the empirical formula. So let's go back to our problem and see if we can find that. There we are. Okay. Oh, CH2. Molar mass equals 12.01 plus 1.008 times 2 is 14.026 grams per mole. All right, that's pretty easy. I'm just going to say, okay, I'm going to take note of that so I don't lose it. We also need the molar mass of the empirical formula. And hopefully these four numbers here, 1, 2, 3, 4, will allow us to find the molar mass of the molecular formula. So I'm going to rewrite those numbers down below so that we have them at handy and at the ready. 4.702 grams.
Like, you tracked it in 4 days, it was just good.
Yeah. Or I could have given you the density and you could have had to find the molar mass. 150.0 kilopascals. And 49.8 degrees Celsius. And I think I actually left a second page because this question takes up so much room. So we do have another blank page after this, so we won't run out of space. All right. So these are the things we have to find the molar mass of the molecular formula. So molecular, it'll be what, sorry? You can do that, or you can, yeah. Molar mass is equal to, Mr. Miyagi puts dirt over his P. So we can find our density.
Oh, yeah.
Which is 4.702. Oh, now this has to be in kilograms, doesn't it? No, it's just grams. Okay, grams. Yes, grams over 1.50 liters. So we have 4.702 divided by 1.5 equals 3.1347 grams per liter. Our temperature is 273.15 plus 49.8 Kelvin, which is 273.15 plus 49.8 is 322.95. And our pressure is 150.0 kilopascals times 1 atmosphere per 101.3 kPa. 150 divided by 101.3 is 1.4808 atmospheres. Good Lord. Okay, so this is then equal to 3.1347 grams per liter times 0.08206 liter atmosphere per mole, -1, Kelvin, -1. And then T is 322.95 Kelvin. Oh God, that's like squishy in there. Okay. Okay. Do you see how I'm kind to whoever would be reading this later by saying, please separate these two sections of things? And then divided by the pressure, which is 1.4808 atmosphere. Let's make sure our units all cancel it correctly. Liters to the -1 cancel with liters. Atmospheres cancel with atmospheres. Kelvin to the -1 cancel with Kelvin. And we are left with grams per mole. Oh, so good, because that's what we want, grams per mole. I know it shouldn't be so exciting, but it is. I get 56.10. Is that what you guys get? Yeah? Okay, that's grams per mole. And now I've run out of space here, so I'm going to say, okay, I have my multiple, whatever that is, multiplier, is the molar mass of the molecular formula over the molar mass of the empirical formula, which is 56.10 grams per mole over, and I circled the other number so I could find it later, 14.026. 14.026 grams per mole. 3.999, which is approximately equal to 4. Actually, it's 9999. So, so now our molecular formula is CH2 times 4, which is going to be C4H8. Hooray! What a relief. It was really long, right? So there is another way to do this if you don't want to use Mr. Miyagi equals dirt over P. You could use these three guys to find moles. And you could take your grams and divide by moles. Does that make sense? You could use PV equals nRT. The pressure was 14.4808. I'm just going to put in the numbers here. I'm not going to bother with the units because we've got like 1 minute left here. How many liters did we have? 1.50 liters. 0.08206 times our temperature, which was 322.95. 322.95. Okay, so that is going to give us our moles. 1.4808 times 1.5, that's a 0, divided by 0.08206 divided by 322.95 is 0.08381. And then I would say my molar mass is my grams over my moles, and my grams was 4.702 grams. over 0.08381 moles equals 56.1. And then we would do the same thing as we did before. I actually found that one a little bit shorter to do it that way. But like, it's nice to have variety just in case you forget one method. You can use the other. Okie dokie. Can I leave you with one of these problems for homework? Since they're so long, just do number 1. Yes? Number 1 on page 33. You guys are awesome. Thank you for your hard work. Thank you for your dedication, showing up so early in the morning. Have a wonderful day.